Quick disclaimer, my slide deck looks very, very different because I was not funded by TIH, at least not for the ventilation projects. I did have a TIH fellowship though, so I have to thank TIH in fact, and I have to thank Professor Leena personally for making the connection where she saw some, synergies between what I was doing in buildings with respect to optimizing comfort and energy and what was going on in the TIH projects. And she made sure I was in conversations with Professor Krishnendu, which is eventually landed me on the ventilation committee now and in the classroom project and in several other opportunities for collaboration. So thank you, Professor Leena, thank you, TIH. And I do have a thank list also. It just comes at the end, unlike the ventilation committee guys who start with the thank list. So it'll come, I'll get there in just a minute. I'm actually a power engineer by training. I'm a power systems engineer. And when I first started this work, I was often asked, what are you doing in comfort and energy? You're an electrical engineer, you're the grid person, you're the big buyers person. Why are you working on this? And so I always have these couple of slides for motivation. Air conditioners are the big need, or any space cooling device is a big need for India. You've seen the kind of March and April we have had. May has been non-existent. May is looking like August. August is coming early in July, June. Things are changing rapidly. We need air conditioners not just for cooling, but for dehumidification so that we can be comfortable. And that is important for us primarily because, at least according to the 2016 data that International Energy Agency had collected, about 10% of the grid peak in India was contributing completely from space cooling and air conditioners. So there was an opportunity, right? If you just do quick calculations, if every 4th air conditioner is turned off, you can shave off about 40 gigawatts of the grid peak that occurred last summer. We had a 252 gigawatt peak last 2024 May. So as a power engineer, I was like, oh, 40 gigawatts, that's so much generation not used, and that's so many savings, roughly speaking, 6.5 crore savings on the cost of energy of, last year it was 7 rupees per kilowatt hour. Therein lies the catch for a power engineer to work in this area, right? And that's how I started working in the area of buildings, and I've been in this area for the past 10 years now. So there's a whole lot of research I want to discuss here based on that experience. Is there scope to do better? Can I really get that 40 gigawatt peak reduction? What do I do? So it helps that there is already so much automation available. There's so much talk of AI. There is so much talk of data science. And to top it all off, anything that you want is smart. Smart cities, smart buildings, smart communities. I take offense to the word smart grid because the grid has always been smart. So, I don't want the grid to get any smarter necessarily. It's already doing a very, very good job. So as a power engineer, I take great offense when somebody says, let's make the grid smarter. I say it's smart enough. But yeah, you could consume better. You could be more responsible in your consumption. And if you can help the grid back, that's a good trade-off. That's what we want to work on, right? Our approach was simple. We want to basically bank in on all the developments that are already happening in the IoT domain. When we first started this work, we started building our own sensors. We created our own, universal remotes of sorts. Then Redmi came up with their phones, which had IR blasters and a whole array of, do you have a, TCL or do you have a Daikin, and then they could configure. And then we said, okay, our remote is not necessarily very useful, but outside of those devices, I think the strength we built through this was in the analytics domain. What you can actually do with the data you're collecting, how you can use it to actuate better. That is where we recognized was our core area of strength, because devices can come and go. We can't necessarily manufacture at the same scale and develop it at the same scale that the industry does. So we started collaborating with more industry partners who gave us end-use devices, and then we would in fact use them to analyze data better, control conditions in the buildings better. So just an instance here, these were our own devices. Anybody who's actually visited the electrical engineering department and visited the GG conference room there we had in fact overfitted the classroom with about 40 odd sensors at different heights, at different spatial distances, just to get an idea of what the temperature and humidity distribution there is going to look like. Remember, this was pre-COVID era for us. We did not care about CO2 at all, only comfort. So only temperature, humidity, these were primary factors for us. And what you can see here, this is a very special room. It has two external walls, which are these, there's the door on this side, and then the walls where you see the air conditioners, those are the two external walls. And you can see these huge temperature gradients. And we weren't quite sure what we are seeing here without monitoring energy. Is it because some of the ACs were off? Is it because the ACs were on but probably not doing a good job? And then that led to another line of reasoning. Can we do health monitoring for air conditioners and so on and so forth as well? But essentially, what we know is we need good visibility of the thermal conditions inside the room to be able to make good decisions with respect to which ACs to keep on, which ACs, and in what modes to use in, right? This gets particularly more complicated when ceiling fans comes in, because very often you're going to find people who are going to say, oh, the draft was too much and I was uncomfortable. Or you're going to find people who are going to say, I was sitting in an air-conditioned room and still sweating. Why does this happen? So you're putting in a lot of energy into actually making people comfortable, but the amount of people who are saying objective achieved typically tends to be a lower fraction. So we want to try to make that gap less and less, right? So we developed sensors and actuators. I don't want to discuss everything that was done. One of the things I think was very important was it's not always necessary to instrument a sensor everywhere you want to have visibility. Sometimes you can build virtual sensors. And we were able to get very good virtual sensors developed for temperature and humidity, where if we had data collected across a variety of conditions, even with just 2 or 3 days of data, we were able to get extremely good data-driven virtual sensors configured, which meant that I can, in fact, visualize what's happening in this room with only 1 or 2 temperature sensors or 1 or 2 TH sensors, and then I can actually predict what that corner is going to look like or what this particular spot in between is going to look like, provided I get some data across 2 or 3 days, okay? So this was important because this helps minimize the sensor footprint. Once we had that data, we could then translate it to more meaningful information. What is comfort here? Are people feeling okay with their thermal environment? Would they want it to be hotter? Would they want it to be colder? What are their preferences? And we've done some work on this using methods such as transfer learning. So if you have data from one environment and with some limited data from a new environment, you can reconfigure a model. So you don't have to always go into a whole data collection scheme where you spend 4 days or a week or so getting the data and then building your model, right? So transfer learning can be used. We've also seen, for example, sometimes rather than go in for all these very complex models, use existing models, but also take some very simple but critical user feedback. You don't ask a user, are you feeling very cold, slightly cold and so on? That's too much. That's too many buckets for them to find themselves in. But if you ask them, do you want it hotter or colder or no change? That's probably easier and that's more useful information to build a good thermal comfort model. My student Ojo is in fact working on it and his first publication should go through soon on this part. He also has a poster outside for you to look. Taking this, we also then, okay, so now you have data, you have an idea of what comfort looks like. Can you use it then to control your air conditioners and your fans better? Because that's the ultimate goal of this whole exercise, right? And so we built simulators. Again, these simulators were not looking at the room as one homogeneous, that it's represented by one temperature. For us, the room actually was represented by multiple local temperature and humidity gradients in different spots. And so that would help us give localized comfort also. There has been some work on this from TCS also, for instance, where they've built patents on the idea of you can seat people according to their thermal preferences, especially in these co-working sort of environments. And so TCS put patents and we put the paper, but I wish I'd thought of the patent before the paper. So, but these are useful again because these are extremely important so that you minimize the instance of someone saying that, oh God, I had the draft coming right on my head, or somebody saying that even in an air-conditioned room I'm sweating, correct? So this helps. We've done this with actual data in the conference room, like I mentioned. We've done this with actual data in some laboratories. We've done this also, not presented here, but a lot of this has also been translated to more simplistic models in actual houses that were built on campus under the solar decathlon competitions. I wear a hat on being a faculty advisor there as well. And this actually works. It can give you a lot of energy savings. So for instance, if you were to wisely choose which areas that are occupied to make comfortable and how, you can absolutely get 5 to 7% savings. And these are savings that come from wise use of information rather than just simply, rules of thumb that the Bijli Bachao Yojana would give, which would just say, change your temperature set point from 25 to 26. Every degree change you do gives you 5 to 6% savings. Not necessarily. It really would depend on what your ambient conditions at that time are going to be, what the thermal load in the room is going to be, and having good visibility of this helps in making better decisions. So where we are headed now is, in fact, facilitating this real-time decision making. All the support that the institute has extended to the TIH projects as well as to the classroom projects that I'm now a part of. This is helping us collect actual, again, data from the field. It is helping us come up with models that can then use that data wisely to decide which ACs to turn on, which fans to turn on, how to make people comfortable. And more interestingly for me, for instance, as an academic, now a new angle is coming up, right? It's no longer just the talk of energy and comfort trade-offs. There's a completely third angle, a non-negotiable angle that comes in the form of the quality of air we breathe, and that's something that's very, very important. Here is my list of all the thanking that I have to do. Professor Mukul Chandorkar, who has been my partner in crime in creating the devices. I have a whole bunch of MTech students to thank here. And in terms of funding, there's of course TIH Imprint, which initially started this in 2016, and industry partners like SAS Labs, who've given me devices free of cost so I could do energy monitoring as well. So thank you very much. I'll take questions at the end.